Hey everyone, and welcome. Today we're going to decode one of the most powerful symbols in all of math. Now, I know it looks a little intimidating, but it's built on an idea so simple, you literally use it every single day, just piling things up. And by the end of this, you're going to see how this one symbol connects everything from viral videos to the fundamental laws of physics. So let's jump in.
So let me start with a quick puzzle for you. What could possibly connect the growth of your savings account, the physics of a sound wave, and the results of a political poll? I mean, on the surface, they seem completely different, right? You've got finance, physics, and people. But there's one single fundamental idea that links them all together. And the answer is, well, it's actually really simple. You understand every single one of them by adding up a bunch of small pieces to see the bigger picture. That's it. That's the secret. The real power isn't in the individual little parts, but in the act of piling them all up.
And this idea of piling up information is exactly where we're going to start. We're going to explore how this simple act of counting actually evolves into this profound way of understanding, well, pretty much everything around us. You see, this concept goes way deeper than just getting a total. It's really about a transformation. Think about it like this. It's the shift from seeing a pile of individual bricks to suddenly understanding the architecture of the entire building. It's the mathematical bridge that takes us from a bunch of isolated parts to a complete functioning system.
Now, to handle all this piling up efficiently, mathematicians came up with a really powerful piece of shorthand, just one single symbol that contains a whole set of instructions. So let's break it down, piece by piece. And here it is, the Greek letter sigma. Yeah, it might look like a strange sideways E, but its job is super simple. It just means add it all up. Think of it as the universal command for combine and conquer. So how does it actually work? Well, first we need a counter. And that's the job of the index, which is usually written as I. Just think of it like a little pointing finger, moving from the first item to the second, then the third, and on, making sure that every single piece gets included in our pile. Next up, we've got to know where to begin. That's the job of the lower bound. It's the starting line for our sum. It just says, hey, start counting from this number. A lot of the time it's 1, but really it can be any number you need it to be. And you guessed it, just like we have a starting line, we absolutely need a finish line. The upper bound tells our little ticker when to stop. As soon as the index reaches this number, the sum is complete. It's the simple instruction that keeps our sum from just going on forever. Okay, so now that we've got the notation down, let's see this thing in action. Because it turns out how you pile things up really, really matters. Using this exact same tool, we can describe very different kinds of growth, everything from a slow crawl to a massive, explosive leap. And this slide shows the two key types perfectly. Over on the left, you've got an arithmetic series. This is that steady, predictable growth, kind of like adding the exact same amount of money to your savings account each month. But then look at the right side. That's a geometric series. This is explosive, compounding growth, where each new step multiplies the last. That's a viral video, see? Same tool, but wildly different results. All right, now we're going to take a bit of a leap. What if we just removed the finish line? What happens when our upper bound is infinity and we just keep adding things up forever and ever? This is where things get really fascinating. A convergent series, on the left, is an infinite sum that somehow still lands on a specific finite number. As you keep adding terms, the total just gets closer and closer to a target until it stabilizes. But a divergent series, on the right, does the opposite. The total just keeps growing and growing forever, shooting off toward infinity. And believe it or not, knowing the difference is crucial for everything from engineering safe bridges to cleaning up audio signals. So we have the symbol, we've got the theory. Now let's connect it all back to the real world and see how this one simple idea truly is an engine for discovery and innovation. This is honestly one of the most beautiful ideas in all of math. So to find the area under that tricky curve, you can start by just approximating it with a few fat rectangles and summing up their areas. The fit, it's not great. So you refine it. You use more but thinner rectangles. The fit gets better. Now, here's the leap of genius. What if you use an infinite number of infinitely thin rectangles? Well, then their sum doesn't just approximate the area. It becomes the exact area. This idea, called a Riemann sum, is the bridge from simple addition to the incredible power of calculus. And this tool is absolutely everywhere. In statistics, finding an average just means summing all the values and then dividing. In computer science, analyzing an algorithm's speed involves summing up all of its individual little operations. And in machine learning, an AI makes a prediction by calculating a massive, massive weighted sum of its inputs. The engine is always the same, piling up pieces of information. So, the crucial takeaway here is that this one concept wears a whole lot of different hats. What a mathematician calls discrete accumulation, a programmer just sees as a loop, and a statistician calls it the mean. But the philosophical interpretation is maybe the most powerful of all. It's the process of the many combining together to create the one. It's how unity emerges from a crowd. So from now on, when you see the sigma symbol, don't just see math homework. See it for what it really is, a lens. It's a powerful tool for taking a complex, messy world, breaking it down into understandable pieces, and then putting it all back together to finally see the big picture. And that leaves us with one final thought. We've seen how this idea works for curves, and data, and finances. But what if we apply that philosophical lens a little more broadly? What if the biggest, most complex systems we see, an entire economy, a society, maybe even consciousness itself, are ultimately just simple sums, waiting for us to figure out what to add up?